Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. More than 4.5 billion years ago, before Earth existed, before the planets took shape, even before the sun ignited with its first nuclear flame, there was only a vast cosmic cloud drifting silently through the Milky Way. This giant cloud, known as a solar nebula, was composed mainly of hydrogen and helium, the two lightest and most abundant elements in the universe, along with tiny amounts of dust, ice, and heavier elements that had been forged in earlier generations of stars. It was cold, dark, and diffuse, spanning many light years in size. A quiet cradle holding the ingredients that would one day become our cosmic home. The story of the solar system's formation is one of motion, case, physics, and time. It is a tale written in the matter that surrounds us today, in the planets, in the moons, in comets that still carry ancient memories, and even within our own bodies, which contain atoms born inside dying stars. Understanding how the solar system formed is not just a journey backward in time, but also a journey toward understanding how worlds like our own come into existence elsewhere in the universe. The nebula that would become our solar system was stable for millions of years, held together by the delicate balance between the outward pressure of its thin gases and the gentle pull of gravity. But such balance cannot last forever. Something needed to disturb this peace. Most astronomers believe that the trigger was the shock wave of a nearby supernova, an exploding massive star that had reached the end of its life cycle. The explosion hurled energy, radiation, and newly formed heavy elements into space, compressing regions of the solar nebula and breaking the calm equilibrium that had existed for so long. Once gravity gained the upper hand, the collapse began. The cloud started to contract inward, accelerating as more mass gathered toward the center. As the nebula collapsed, it began to spin faster, just like an ice skater spinning faster when pulling their arms inward. This rotation flattened the cloud into a spinning disk of dust and gas known as a protoplanetary disk. At its center, most of the mass accumulated to form what would become the sun, while the remaining material spread out across the disk, awaiting its future transformation into planets and other celestial bodies. Inside the growing center of the nebula, temperatures rose drastically. Hydrogen atoms were squeezed together with increasing pressure until nuclear fusion ignited. This was the birth of the sun, a new star shining with intense heat and light. The ignition of fusion released a wave of radiation and a powerful solar wind, a stream of charged particles that blasted outward and began clearing the inner disk of light gases. The emergence of the sun was the defining moment that gave structure to the forming solar system. Gravity now held everything in a new order, bound together by the sun's massive pull. Meanwhile, farther from the center, where temperatures were lower, tiny grains of dust began colliding and sticking together through a process known as accretion. Over time, these particles grew from microscopic specks into larger pebbles, rocks, and eventually kilometer-sized planetesimals. These objects were the first solid building blocks of planets. Their collisions were sometimes gentle enough to allow growth, but often chaotic and violent, breaking apart newly formed bodies and scattering debris in every direction. It was a cosmic construction zone filled with both progress and destruction. In the inner solar system, where heat from the sun was intense, volatile materials like water and methane evaporated, leaving behind mostly metals and silicate rocks. This is why Mercury, Venus, Earth, and Mars, the four terrestrial planets, are small, rocky, and dense. Their formation required repeated collisions among planetesimals, slowly merging into larger protoplanets with stronger gravitational influence. The young Earth, for example, likely formed through dozens of major impacts, each event reshaping its structure, heating its interior, and adding mass from the broken remains of smaller worlds. Farther from the sun, beyond the frost line, temperatures were lower and ices could survive. Here, planetesimals grew much larger and faster, accreting not only dust and rock, but also ice. As these icy worlds expanded, their gravity became strong enough to attract massive envelopes of hydrogen and helium from the surrounding disk. This is how the gas giants Jupiter and Saturn came to be. They formed their thick, swirling atmospheres early, while the nebula still contained abundant light gases. Their sheer size and immense gravity would later play a crucial role in shaping the architecture of the solar system, influencing the orbits and evolution of countless smaller bodies. Even farther out, where material was scarce and freezing temperatures dominated, the ice giants Uranus and Neptune emerged. They formed more slowly than their larger siblings, accreting less gas before the solar wind cleared the remaining nebular material. Their composition reflects this different environment, containing more ice and heavier elements relative to hydrogen and helium. Together, the four giant planets, Jupiter, Saturn, Uranus, and Neptune, became guardians of the outer solar system, shaping the motions of comets, dwarf planets, and the icy bodies beyond. While planets were taking shape, the leftover debris scattered throughout the young solar system formed belts and reservoirs of small bodies that still exist today. Between Mars and Jupiter, the asteroid belt became home to countless rocky fragments that never fully merged into a planet, largely due to the disruptive gravitational influence of Jupiter. Far beyond Neptune, in the frozen outskirts of the solar system, lies the Kuiper Belt, populated with icy worlds, including Pluto and many other dwarf planets. And even farther, extending halfway to the nearest stars, is the Oort cloud, a vast spherical shell of comets that remains a distant and unseen reminder of the solar system's early chaos. As the planets grew, the young solar system was still far from peaceful. The era known as the Late Heavy Bombardment brought intense waves of impacts across all newly formed worlds. Asteroids and comets frequently smashed into planets and moons, leaving behind scars seen today as craters. Earth experienced this violent phase as well, and although we no longer see most of its ancient craters, erased by tectonics, weather, and oceans, these collisions played a critical role in shaping the planet's future. They delivered water and organic molecules, the essential ingredients for life, possibly carried from far beyond the frost line by icy comets. Without these cosmic deliveries, Earth might have remained a dramatically barren world. One of the most dramatic events in this violent era involved the early Earth and a Mars-sized protoplanet, often referred to as Theia. In a catastrophic collision, Theia struck Earth with immense force, ejecting molten debris into space. This material eventually coalesced into our moon. The giant impact not only gave Earth its natural satellite, but also altered Earth's rotation, tilt, and evolution. The moon's stabilizing influence has helped maintain relatively calm seasons and ocean tides, shaping the long-term environmental conditions that allowed life to flourish. Even after the moon-forming impact, Earth remained a molten world for millions of years. Gradually, its surface cooled, forming a solid crust. Volcanoes erupted constantly, releasing gases that formed the early atmosphere. As temperatures fell and water vapor condensed, the first oceans emerged. Meanwhile, sunlight continued to stream across the solar system, and the sun, still young, was more active than it is today. It emitted strong solar winds and ultraviolet radiation, gradually stripping away the atmospheres of smaller worlds that lacked strong magnetic fields. This is why Mercury became an airless, scorched surface, while Mars, once warm and wet, ultimately lost much of its atmosphere and water to space. Each planet developed a unique identity shaped by its position, size, composition, and geological activity. Although they all formed from the same cloud of material, their evolutionary paths diverged dramatically. Venus, similar in size to Earth, transformed into a hostile world with crushing air pressure and runaway greenhouse heating. Mars cooled rapidly, its once dynamic interior fading into dormancy as volcanic and magnetic activity declined. Jupiter's massive gravity sculpted the orbits of countless smaller bodies, establishing resonances and clearing gaps in the asteroid belt. Saturn developed its magnificent ring system, which may have formed from shattered moons or icy debris left over from collisions. Uranus tilted sideways, likely the result of a colossal impact, giving its seasons more extreme than anywhere else. Neptune's strong winds and dynamic atmosphere continue to surprise scientists with their power and unpredictability. All these differences remind us that the solar system's formation was not a neat or uniform process, but a chaotic, evolving dance influenced by gravity, heat, chemistry, and chance. During the early ages of growth, countless protoplanets either merged or were flung out of the solar system entirely. Some became permanent wanderers in interstellar space, carrying the history of our solar system beyond its borders. Others were captured by the gravity of giant planets and now exist as irregular moons. The solar system we see today is only the final version of a natural selection process among billions of pieces of initial material. The sun itself continued to evolve as well. Once fusion stabilized in its core, it entered a long life as a main sequence star, shining steadily and providing energy to its surrounding planets. But even as the sun's brilliance nourished the young solar system, it also sculpted it through radiation pressure, driving away leftover gas and dust. Within a few million years, the protoplanetary disk was mostly cleared. Planets, moons, and smaller objects remained as the lasting architecture, while the raw nebular material that once filled the solar system faded into the distant void. What followed was a long age of cooling and settling. On Earth, the surface slowly transformed into continents and oceans. Impact rates declined over time, allowing life's earliest building blocks to take root. Chemical reactions in the oceans, fueled by heat from the planet's interior and energy from the sun, may have sparked the formation of primitive molecules capable of self-replication. Life emerged, and a new chapter in the evolution of the solar system began. One that would eventually lead to intelligent beings capable of looking back and asking how it all started. But even now, long after the early chaos has passed, remnants of the solar system's violent youth continue to move across space. Asteroids occasionally collide with planets. Comets from the Kuiper Belt or Oort cloud swing inward on elongated orbits, putting on a show of glowing tails. Meteorites rain down on Earth, many of them billions of years old, providing invaluable insight into the earliest materials that built the planets. These fragments are untreated fossils from the dawn of the solar system, offering a direct connection to our past. Our understanding of how the solar system formed has grown from careful observations, spacecraft exploration, laboratory studies of meteorites, and powerful computer simulations. Modern telescopes allow astronomers to watch young planetary systems forming around distant stars, giving us a chance to witness processes similar to those that shaped our own cosmic neighborhood. In these swirling disks of dust and gas, we see the same physics at work: gravity gathering material into clumps, collisions and growth leading to planet formation, and radiation clearing away debris as new stars ignite. The solar system's story, once a mystery hidden in ancient rock and distant space, is now being revealed piece by piece. Yet even with all this knowledge, many questions remain. How exactly did the initial distribution of material shape the differences between planets? Why did Earth end up with so much water, while Venus and Mars did not? What caused the precise arrangement of giant planets? And did they migrate significantly after forming? Evidence suggests that Jupiter and Saturn may have shifted positions over time, disturbing the orbits of many smaller bodies and causing waves of impacts that reshaped the inner solar system. This idea, often called the NICE model, proposes that the late heavy bombardment was triggered by the gravitational migration of giant planets, scattering asteroids and comets in every direction. Studying the smallest objects, such as comets, is particularly valuable because they preserve pristine material from the earliest days of the solar system. Missions like Rosetta, which landed on the comet 67P Churyumov-Gerasimenko, have allowed scientists to directly measure the chemical composition of these icy bodies. Many comets contain complex organic molecules, supporting the theory that ingredients for life may have been transported to Earth from distant regions of the solar system. Meanwhile, NASA's OSIRIS-REx mission returned samples from asteroid Bennu, providing further insight into the early composition of rocky materials and the effects of billions of years of radiation and weathering in space. The solar system's formation is not just ancient history, it continues to evolve even today. Gravitational interactions subtly alter planetary orbits over long timescales. Tidal forces reshape moons and drive geological activity, such as the volcanic eruptions on Io or the hidden ocean beneath Europa's icy shell. Saturn's rings lose material over time and may eventually disappear. New collisions in the asteroid belt create fresh fragments, while radiation gradually breaks down cometary nuclei into smaller pieces. The story of the solar system is ongoing, an ever-changing system bound together by the enduring power of gravity and the radiant energy of our sun. As we explore farther and learn more, we come to appreciate not only the vast physical processes that built the planets, but also the delicate balance that allowed life to flourish here on Earth. If Earth had formed slightly closer or farther from the sun, if the moon had never existed to stabilize its tilt, if Jupiter had not intercepted countless dangerous asteroids, or if water had not been delivered to the surface, the story of our world might have been very different. The solar system's history is filled with moments where tiny differences produced enormous consequences. Every planet, every moon, every comet is a chapter in that remarkable story. Human curiosity has driven us to seek answers beyond our planet, and each discovery brings us closer to understanding our origins. The solar system is not just a collection of celestial objects, but a family born from the same cosmic cloud, shaped by shared forces, connected by gravity, and illuminated by the sun's eternal glow. When we gaze at the night sky, we are looking into a timeline that stretches back billions of years, into a history that continues to unfold with each new mission and observation. As we deepen our understanding of the solar system's origins, we also uncover clues about how common or rare systems like ours might be in the universe. Astronomers have discovered thousands of exoplanets orbiting distant stars, and some of these worlds exist in systems very different from our own. There are planets larger than Jupiter orbiting scorchingly close to their parent stars, known as hot Jupiters. There are super-Earths, rocky worlds larger than Earth but smaller than Neptune, a type of planet that does not exist in our solar system. There are planets with elliptical orbits, planets in binary star systems, and planets that may be covered entirely by oceans or wrapped in thick, toxic atmospheres. Observing these systems allows scientists to test theories of planet formation and ask why our solar system took the particular form that it did. The formation of the solar system was governed by universal principles of physics, gravity, angular momentum, thermodynamics, and chemistry, but its exact outcome was influenced by countless variables and random events. A slightly different impact here, a slightly different migration path there, and an entirely different arrangement of planets might have emerged. The uniqueness of the solar system does not make it any less connected to the universe. Instead, it highlights the infinite possibilities that arise from the same cosmic ingredients. Every star that is born has the potential to form its own family of worlds, each with its own story shaped by chance and physics. Looking backward in time is not the only way to understand the solar system's formation. We can also look forward. Knowing how the solar system formed gives us predictions about its long-term future. The sun is about halfway through its life as a main sequence star. In roughly 5 billion years, its core will run out of hydrogen fuel, causing the sun to expand into a red giant. This transformation will engulf Mercury and Venus, and possibly Earth. The outer planets will drift farther away as the sun loses mass. After shedding its outer layers, the sun will eventually shrink into a white dwarf, leaving behind a ghostly shell of gas known as a planetary nebula. The story of the solar system, just like its beginning, will be marked by dramatic change. Despite these distant and unavoidable transformations, the current moment in the solar system's timeline is one of relative stability. The planets follow predictable paths. The sun shines steadily. Life thrives on Earth. But it is humbling to realize that this calm era is temporary, just one short chapter in a history that spans billions of years. The knowledge of how the solar system formed allows us to appreciate our place in time, living during a rare and fortunate period where conditions are just right for life to flourish and for humans to look outward and study the cosmos that created us. The clues to our origins are not hidden only in distant space. They are also locked deep within Earth itself. By studying the isotopes of elements found in ancient rocks, scientists can trace when and how these materials formed. Some isotopes reveal the heat and pressure conditions during planetary differentiation, when heavy metals like iron sank to form Earth's core and lighter materials rose to form the crust. Others record the catastrophic impacts that delivered new materials and reshaped the planet. Every grain of sand, every drop of water, every atom in our bodies carries a history that leads back to the collapsing nebula that once drifted silently through space. Meteorites offer a more direct window into the early solar system. Some types of meteorites, known as chondrites, are considered the most primitive materials we can study. They have remained largely unchanged since the solar system's infancy. Embedded within them are chondrules, tiny spheres of melted rock that once floated freely in the protoplanetary disk. Trapped in their mineral structures are records of radioactive decay that provide precise ages for the earliest solid matter. These measurements suggest that the first solid grains began forming around 4.567 billion years ago, marking the beginning of the solar system's timeline. Other meteorites show signs of having come from differentiated worlds, protoplanets that partially melted and separated into layers like tiny versions of Earth before meeting their violent ends through collisions. One of the most important discoveries in the study of planetary origins is that the materials forming Earth originally came from all across the solar system. This means that rather than building a planet exclusively from local dust, early Earth collected material through chaotic, wide-ranging collisions and gravitational interactions. Some of the water now in Earth's oceans may have arrived on comets or icy asteroids flung inward from the outer solar system. Complex organic molecules essential for life may also have formed far from the sun and later arrived on Earth through impacts. In a sense, the building blocks of life were cosmopolitan, traveling vast distances before eventually combining to create a world rich with oceans, forests, and living beings capable of contemplating their own origins. The story of the solar system's formation is also written on the surfaces of other planets and moons. Some moons of the outer planets, such as Europa, Enceladus, and Titan, preserve environments and materials from ancient times. Beneath the icy crust of Europa lies a global ocean that may have existed for billions of years, warmed by tidal forces rather than sunlight. Geysers on Enceladus eject plumes of water vapor and organic compounds into space, hinting at hydrothermal vents deep below. Titan, with its thick nitrogen-rich atmosphere and liquid hydrocarbon lakes, offers an intriguing analog for early Earth before oxygen transformed our planet. These worlds invite us to study how planetary environments evolve and to search for traces of life beyond our own. Moons closer to the sun hold different clues. Earth's moon preserves a nearly untouched record of the late heavy bombardment, because unlike Earth, it lacks weather and plate tectonics that would erase impact craters. Mercury's iron-rich core and thin crust hint at violent stripping of its outer layers, possibly from a giant collision. Mars, with valleys carved by ancient rivers and sediments laid down in vanished lakes, tells a story of a planet that once resembled Earth, but suffered a tragic loss of habitability. Venus, wrapped in clouds of sulfuric acid and broiling under intense heat, may once have had water and milder temperatures before experiencing runaway greenhouse conditions. All these outcomes formed from the same starting conditions, yet resulted in wildly different planetary destinies. When we study how the solar system formed, we are ultimately studying why Earth is the way it is. Every twist in the early history of planet formation influenced whether our world would be habitable. The presence of Jupiter may have shielded Earth from constant bombardment, allowing life to eventually thermify. The stabilizing effect of the moon on Earth's axial tilt reduced climate chaos and helped maintain a stable environment for billions of years. The distribution of heat from the sun placed Earth in the right region for liquid water. Even the catastrophic impact that created the moon helped establish the planet we know today, with a core generating a magnetic field that protects the surface from solar irradiation. The solar system's formation is not just a cosmic event. It is the foundation of everything that makes Earth special. As scientists uncover more details about the formation of the solar system, they also learn how fragile the balance of conditions truly was. The distance of Earth from the sun, the composition of its atmosphere, the presence of its magnetic field, and the contributions of countless collisions all played a role in making our planet a cradle for life. If any of these factors had been slightly different, Earth might have become a frozen wasteland like Europa or a scorched inferno like Venus. The solar system's formation produced not only a planet capable of supporting life, but also a complex chain of events that made intelligent life possible. This understanding inspires us to explore worlds beyond our own, searching for not just planets, but for stories similar to ours waiting to unfold. The outer regions of the solar system hold some of the most intriguing remnants of planetary formation. The Kuiper Belt, a wide ring beyond Neptune, contains leftovers from the early days that never found a home in a major planet. Dwarf planets like Pluto, Eris, Makemake, and Haumea represent a class of icy bodies that reflect what the solar system could have been if more mass had accumulated in those distant regions. Some Kuiper Belt objects are binary systems, with two bodies of similar size orbiting each other, suggesting varied formation histories. Many of these worlds remain unexplored, their surfaces cloaked in mystery, their compositions and geological activity still unknown. Even more distant is the Oort cloud, a theoretical swarm of icy bodies forming a spherical shell around the solar system. Although no spacecraft has yet seen an object in the Oort cloud directly, the long-period comets that occasionally appear in the inner solar system strongly suggest its existence. These comets have such elongated orbits that they take millions of years to return from their distant travels. They are believed to be leftovers scattered by the giant planets during their formation, ejected into far-off regions where they became gravitationally bound to the sun, but remain at the very edge of interstellar space. The Oort cloud is a silent reservoir of the solar system's oldest and most primitive material, a cosmic time capsule waiting to be opened by future exploration. Space missions have allowed us to revisit the solar system's earliest eras through direct investigation. The Voyager spacecraft, launched in 1977, continue their journey beyond the heliosphere into interstellar space, carrying with them instruments that measure the boundaries of the solar system's influence. These spacecraft were not designed to study planet formation specifically, but their longevity and distance provide essential context for understanding the environment that surrounds our planetary system. Missions to Mars, Venus, Mercury, and the outer planets return data that help refine our theories and challenge old assumptions. Each spacecraft that visits a new world uncovers surprising details that force scientists to adjust their models of how the solar system evolved. One of the greatest scientific achievements in this field has been the detection and analysis of protoplanetary disks around young stars. Using advanced telescopes such as ALMA, Atacama Large Millimeter/Submillimeter Array, astronomers can observe these disks and watch planets being born in real time. They see rings and gaps that reveal where worlds are taking shape, zones of dust accumulation and where planetesimals grow, and regions where heat from the star pushes lighter gases outward. These observations are the closest we have come to witnessing our own solar system's ancient past. They confirm that planet formation is a natural and widespread process, one that likely occurs around stars across the galaxy. Yet, planet formation is not always successful. Many protoplanetary disks fail to produce planets or produce only small ones. Some planets may be destroyed in collisions or fall into their stars during migration. Others may be violently ejected into interstellar space. The solar system's existence as a stable, multi-planet family required extremely precise timing and favorable outcomes. Even among successful systems, the final arrangement of planets varies widely. The more we study, the more we learn that the solar system is just one possible result among countless outcomes shaped by physics and chance. An important clue to how the solar system formed lies in its chemical composition. Scientists analyze the ratios of elements such as carbon, nitrogen, silicon, and iron in different planets, moons, and meteoritic materials. These patterns reveal how temperature and distance from the sun influence the distribution of elements in the protoplanetary disk. They also show evidence of contributions from previous supernovae, suggesting that the solar system formed in a region rich with recycled stardust from earlier generations of stars. This cosmic recycling means that every planet in the solar system contains atoms forged in long-dead stars, connecting our origins to the broader history of the universe. Perhaps the most profound realization from studying planetary formation is the connection between cosmic processes and life. The stars that lived and died before the solar system provided the heavy elements necessary for biology. The physical forces that shaped planets allowed Earth to develop oceans and an atmosphere. The collisions that delivered water and organic molecules enabled chemistry to evolve into biology. And once life began, the stable conditions of the solar system allowed evolution to unfold over billions of years, producing organisms capable of observing the cosmos and asking where they came from. The formation of the solar system is therefore not just a scientific event, but a deeply philosophical one. It is the beginning of a story that includes everything: planets, stars, oceans, trees, civilizations, and the very curiosity that drives scientific inquiry. Today, humans are no longer passive observers of the solar system's story. We are active participants. Through exploration and innovation, we extend our presence beyond Earth. Robotic explorers roam Mars, dive through Titan's atmosphere, and skim past comets. Telescopes study worlds light years away. Private companies plan missions to mine asteroids, altering the material flow of the solar system for the first time in its history. Each step brings us closer to becoming a multi-planet species, one that might eventually shape the future of other worlds, just as physics shaped the past of this one. As humanity expands its reach, understanding the solar system's origins becomes even more important. If humans are to live on Mars or build habitats in the asteroid belt, we must know the geology, resources, and long-term stability of these places. If we are to search for life beyond Earth, we must understand which environments support biology and which do not. Studying the solar system's formation offers clues to where life is most likely to emerge, both here and around other stars. Every new discovery helps to refine our strategies for exploration and increases the chances that we may one day find other living worlds. Modern technology is unlocking new ways to trace the solar system's evolution. Simulations allow researchers to recreate billions of years of motion and collisions, testing hypotheses about how planets migrated and how minor bodies were scattered. Spectroscopy allows scientists to detect the presence of ice, minerals, and organic compounds on distant objects. Sample return missions provide physical materials that can be studied in laboratories, revealing chemical signatures imprinted in ancient times. With each advancement, the picture of the early solar system becomes clearer, though there will always be complexities that resist easy explanation. What makes the solar system's story particularly compelling is that it is still being written. The sun continues to fuse hydrogen into helium, slowly changing its luminosity. Earth's interior remains active, driving plate movements and volcanic eruptions. Moons like Io and Enceladus experience tidal heating, creating environments that defy expectations. The asteroid belt provides both danger in the form of potential impacts and opportunity through resources that could support future industry in space. The Kuiper Belt reveals dynamic processes among icy bodies far from the sun's warmth. The Oort cloud sits silently, waiting for the occasional gravitational nudge that will send a comet rushing inward across the solar system's vast expanse. The delicate balance of forces that shape the solar system also highlights the interplay between chance and necessity in cosmic evolution. Gravity, the fundamental sculptor of planetary systems, drew matter together into dense clumps and organized orbits. Angular momentum dictated the disk's rotation, flattening the protoplanetary cloud into a plane in which planets could form. Collisions, both constructive and destructive, determined which objects survived to become planets, moons, or minor bodies, and which were shattered or ejected into interstellar space. Radiation from the young sun drove off excess gas, clearing the way for planets to stabilize in their eventual orbits. Chemical gradients dictated which materials condensed at specific distances, creating rocky worlds near the sun and icy giants further out. Together, these forces produced a system of remarkable order, yet one that emerged from an environment of chaos and violence. Even small differences in initial conditions could have led to radically different outcomes. Had the early solar nebula been slightly more massive, the inner planets might have grown into gas giants, or the sun itself might have become a more massive, short-lived star incapable of supporting stable planets over billions of years. Had a nearby supernova been closer or more intense, the collapse of the nebula might have been disrupted entirely. The formation of a system like ours depends not only on universal laws, but also on a chain of fortunate events, which in turn allowed Earth to become a haven for life. The planetary arrangement we see today is also the product of dynamic interactions that occurred long after initial formation. Migration of giant planets, gravitational resonances, and collisions sculpted the current positions of planets and minor bodies. Jupiter's immense gravity influenced the asteroid belt, preventing a planet from forming between Mars and itself, and shepherded objects into stable orbits, such as the Trojan asteroids. Neptune's outward migration likely triggered the scattering of many Kuiper Belt objects, some of which became long-period comets that periodically visit the inner solar system. These migrations highlight the fact that planet formation is not a static event, but an ongoing evolution over millions of years. Moons and satellites provide further insight into the early processes of planetary development. Many of the solar system's moons form from the same material as their parent planets, while others were captured or resulted from giant collisions. Ganymede, Callisto, and Europa, moons of Jupiter, form from the circumplanetary disk surrounding the young gas giant, mirroring the larger-scale formation of planets around the Sun. Their internal structures and compositions provide clues to the conditions in the outer solar system during the time of planet formation. Similarly, Saturn's moons, including Titan and Enceladus, reflect the complex interplay of ice, rock, and internal heat that shape many small worlds. Understanding the formation of the solar system also requires studying the small, icy bodies that preserve the oldest material. Comets act as time capsules, retaining the chemical and isotopic signatures of the earliest solar nebula. Missions such as Rosetta and Deep Impact reveal complex organic molecules. Water ice, in a surprisingly active geological history even on these tiny bodies. Meteorites, particularly carbonaceous chondrites, retain records of chondrules and calcium-aluminum-rich inclusions, the first solid condensates in the solar nebula. By analyzing their isotopic compositions, scientists can reconstruct timelines of planetary formation and understand the sequence in which elements condensed and were incorporated into larger bodies. The story of planetary formation is also a story of transformation. Dust and gas became pebbles. Pebbles became planetesimals, and planetesimals became planets through billions of years of accretion. Differentiation inside planets separated dense metal cores from silicate mantles, setting up magnetic fields and geological activity. Giant impacts reshaped worlds and even created moons. Volatile delivery from outer regions supplied water and organics. The evolution of planets and their satellites was an interconnected process, with events on one world influencing others through gravity, collisions, and the scattering of material across the solar system. Even the Sun's own evolution played a decisive role. During its early T-Tauri phase, the Sun's strong solar wind removed much of the remaining gas from the disk, preventing the formation of additional massive planets and shaping the final architecture of the system. Solar radiation influenced chemical reactions in the disk, altering the composition of grains and ices. The Sun's increasing luminosity over time affected planetary climates and the retention of volatile substances. Without the Sun's precise mass, energy output, and stability, the planets may not have developed the conditions that allowed complex chemistry and life to flourish. Life itself, intimately linked to the solar system's formation, illustrates the consequences of planetary and stellar processes. The right combination of water, temperature, atmosphere, and protection from solar and cosmic radiation created an environment suitable for organic molecules to assemble and evolve. Earth's geological activity recycled materials and maintained the carbon cycle, regulating the climate over millions of years. Impacts and volcanic activity delivered energy and new materials to early life, while Jupiter and Saturn shielded Earth from frequent catastrophic collisions. In this way, the story of the solar system is inseparable from the story of life, highlighting the delicate balance between cosmic forces and the emergence of biology. The ongoing exploration of the solar system continues to refine this story. Robotic probes, sample return missions, and telescopic observations reveal unexpected complexity in even the smallest objects. Asteroids thought to be inert show signs of activity, comets reveal dynamic jets, and moons that appear frozen are geologically alive. Each discovery adds depth to our understanding of how planets formed and evolved, showing that the solar system is a living laboratory where the principles of physics, chemistry, and geology are continually at work. In contemplating how the solar system formed, it becomes clear that we are both witnesses and participants in a process billions of years in the making. The atoms in our bodies were forged in stars that lived and died long before the sun ignited. The water we drink may have been delivered by comets and asteroids that traveled across the young solar system. The landscapes we inhabit were shaped by tectonics, volcanism, and impacts that began when the solar system was still young. Every element of our environment carries the signature of these ancient processes, linking us directly to the cosmic events that created our world. The formation of the solar system is not just a scientific narrative, but a cosmic story that connects all matter in our corner of the universe. It demonstrates how order can emerge from chaos, how life can arise from inanimate materials, and how the smallest variations in physical conditions can have profound consequences. By studying this process, we gain insight not only into the history of our own planet, but also into the potential for worlds elsewhere, the likelihood of life beyond Earth, and the forces that continue to shape the cosmos. As we look toward the future of the solar system, it is clear that change is inevitable, yet the forces that shaped it billions of years ago continue to operate today. Planetary orbits slowly shift due to gravitational interactions, and minor bodies are perturbed by collisions or by passing stars. Asteroids may impact planets, comets may bring fresh material from the distant reaches, and the sun itself will gradually evolve, changing the energy balance that sustains life on Earth. While these changes occur over immense timescales, they remind us that the solar system is not static. Its formation was just the beginning of a story that is still unfolding, written in the motions of planets, the impacts of celestial bodies, and the ongoing transformation of matter. The solar system structure today, rocky inner planets, massive gas and ice giants, belts of small bodies, and distant icy reservoirs, reflects the delicate interplay of the processes that began in the solar nebula. Each component carries evidence of its origins. The composition of planets reveals temperature gradients in the protoplanetary disk. Moons preserve histories of collisions and accretion. Asteroids and comets hold primordial material dating back to the solar system's infancy. By studying these objects, scientists are not just reconstructing the past, they are tracing the pathways that led to Earth's habitability and to the emergence of life. The solar system is, in essence, a cosmic laboratory, showing how matter organizes itself into complex systems under the laws of physics. Exploration of other planetary systems around distant stars further illuminates the uniqueness and universality of the solar system's formation. Observations reveal that while the physics is the same, gravity, accretion, and radiation shaping disks into planets, the outcomes vary dramatically. Some systems host massive planets orbiting extremely close to their stars, while others have densely packed multi-planet systems. These discoveries emphasize that our solar system is only one possibility among countless outcomes, a remarkable arrangement that has produced conditions suitable for life. By comparing our system to others, scientists gain insight into the processes that favor the formation of habitable worlds and the factors that determine planetary diversity. The story of the solar system is also one of resilience and adaptation. Over billions of years, planets and moons have survived collisions, migrations, and solar evolution. Earth, in particular, has endured impacts, climate shifts, and geological upheaval, all while maintaining conditions that support life. This resilience highlights the intricate balance of forces and events required to produce stable, life-friendly environments. It also underscores the interconnection between cosmic history and biological evolution. The emergence of life depended on the precise outcome of the solar system's formation, just as life itself now becomes a record of the system's dynamic past. In contemplating the solar system's formation, we gain not only scientific knowledge, but also perspective on our place in the universe. The atoms in our bodies originated in ancient stars. The water we drink arrived from distant icy bodies, and the land we inhabit was shaped by cosmic collisions and geological processes. Our existence is intertwined with the events that unfolded in the solar nebula billions of years ago. Understanding these events deepens our appreciation of Earth's uniqueness, of the delicate conditions that sustain life, and of the interconnectedness of all matter in the cosmos. Looking ahead, humanity's role in the solar system may become more active. Future missions may exploit asteroid resources, establish habitats on the Moon or Mars, and even venture to the distant icy worlds of the Kuiper Belt. Each of these activities will add a new chapter to the solar system's story, demonstrating that while its formation billions of years ago was governed by natural forces, its future will increasingly be shaped by intelligent beings who emerged as a consequence of those very forces. By studying the origins of the solar system, we equip ourselves to responsibly participate in its ongoing evolution, understanding the risks and opportunities inherent in our cosmic neighborhood. The solar system's formation is a testament to the beauty and complexity of the universe. From a diffuse cloud of gas and dust, through the violent collisions and accretion of planetesimals, to the emergence of planets, moons, and smaller bodies, it is a story of transformation, balance, and dynamic evolution. The processes that created the solar system are universal, yet their outcomes are profoundly diverse, producing worlds that range from scorched deserts to frozen oceans, from tiny moons to massive gas giants. Earth, uniquely positioned and endowed with life, serves as a reminder of the extraordinary circumstances that can arise from cosmic forces. Ultimately, understanding how the solar system formed allows us to trace the chain of events that led to the existence of our world, our lives, and our curiosity. It links us to the stars that lived and died before the sun, to the nebular cloud that collapsed to form the planets, and to the collisions, migrations, and transformations that shape the architecture we see today. It reminds us that we are part of a continuum of cosmic history, and that by studying the solar system, we not only uncover the secrets of the past, but also gain insight into the forces that will shape its and our future. The story of the solar system's formation is, in every sense, the story of us, written in the language of physics, chemistry, and time, unfolding across billions of years and continuing as long as the sun shines on the worlds it created.